There is a place where the sun runs out of power, where its wind, the constant stream of charged particles it has been exhaling for billions of years, simply stops, where the last traces of our star's influence collide with something older, colder, and far more powerful. For most of human history, we had no idea what that place actually looked like. We had theories, we had models, we had educated guesses drawn on whiteboards in laboratories, and then we sent something there. Voyager 2 has been drifting through space since 1977. It has crossed the orbit of every planet in our solar system. It has photographed worlds no human eye had ever seen in detail. And in November of 2018, it crossed a line that no human-made object had ever crossed with its full suite of instruments intact. It crossed into interstellar space. What it found there was not what anyone predicted. Not a gradual thinning of solar influence, not a slow drift from one environment into another. What Voyager 2 detected at the edge of everything we call home was abrupt, sharp, and in some ways deeply unsettling. Plasma collapsed, cosmic rays surged, magnetic fields snapped to a new orientation, and buried in the data were anomalies that physicists are still struggling to fully explain. Let's go back to the beginning. In the summer of 1977, two spacecraft left Earth within weeks of each other. Their primary mission was straightforward on paper: fly past Jupiter and Saturn, take some pictures, collect data, report back. But there was a rare planetary alignment happening, a configuration that only occurs once every 175 years that allowed something extraordinary. Using gravitational assists, a spacecraft could slingshot from one planet to the next, threading a path through the outer solar system that would otherwise be physically impossible. NASA called it the Grand Tour, and Voyager 2 was going all the way to the end of the line. Jupiter came first, and right away the solar system stopped being the quiet place we thought it was. Jupiter was not a passive giant. It was electrically violent. Lightning crackled through its clouds in sustained storms, unlike anything ever detected on Earth. Radio signals called whistlers, the electromagnetic fingerprint of lightning, were streaming out of a place we assumed was just a ball of gas. Then came Io. At the time, moons in the outer solar system were expected to be geologically dead. Cold, cratered, silent, Io had no business being active. But it was erupting, violently, plumes of sulfur dioxide shooting hundreds of kilometers into space. It was the first time volcanic activity had ever been observed on another world. In a single flyby, our entire picture of what a moon could be was redrawn. Then Saturn, winds screaming at nearly 1,700 kilometers per hour, rings revealed not as smooth disks, but as thousands of intricate ringlets with strange, ghostly spokes, radial streaks that appeared and vanished in defiance of basic orbital mechanics. And at the North Pole, a hexagon, a six-sided atmospheric wave pattern nearly 30,000 kilometers across, each side longer than the diameter of Earth, that has persisted for decades and that scientists still cannot fully explain. But unlike Voyager 1, which pushed outward after Saturn, Voyager 2 kept visiting planets. Uranus in 1986, Neptune in 1989. Two worlds no spacecraft had ever seen up close. Uranus turned out to be magnetically broken. Its field is tilted nearly 60 degrees off its rotational axis and offset from the planet's center entirely, creating a magnetic tail that twists into a corkscrew as the planet rotates. It is also the coldest planet in the solar system, barely emitting any internal heat, for reasons we still don't fully understand. Then Neptune, winds exceeding 2,000 kilometers per hour. The fastest ever recorded anywhere in the solar system, on a planet receiving barely any solar energy to drive them. And Triton, Neptune's largest moon, was erupting geysers of nitrogen gas from a surface frozen to within 30 degrees of absolute zero. Active geology on one of the coldest worlds we've ever visited. By the time Voyager 2 cleared the planetary neighborhood, it had delivered more paradigm-shifting discoveries than any other spacecraft in history, and it was still going. Then in November 2018, everything changed again. The solar wind instrument stopped detecting solar particles. Not gradually, it stopped. Over just a few days, the outward flow of solar wind that had been measured continuously for 41 years simply ceased. At the same moment, cosmic ray counts spiked sharply. High-energy particles from distant supernovae and violent galactic events, normally held back by the heliosphere's protective bubble, were flooding in. Voyager 2 had crossed into interstellar space. What made this crossing historically unique was that Voyager 2's plasma science instrument was still functioning. When Voyager 1 crossed the boundary 6 years earlier, that instrument had already failed, meaning scientists had to infer plasma conditions indirectly. This time they could measure it directly, and the data immediately produced surprises. The temperature beyond the heliopause was lower than expected, the plasma density was higher, and the boundary itself was far sharper than theoretical models had predicted. There was no gradual blending of environments. Cross the line and you were in a completely different cosmic regime almost instantly. But beyond the heliopause, instead of clean empty space, Voyager 2 detected additional structure, layers of compressed plasma, regions where the magnetic field behaved differently. The boundary wasn't a single clean line, it was a layered dynamic interface, like the edge of a river where the current and still water create eddies rather than a clean separation. This matters because it dismantles the simple picture we had of the heliosphere. We imagined our solar system as a bubble floating freely through interstellar space, solar wind pushing outward symmetrically in every direction. But Voyager 1 and Voyager 2 crossed the boundary at different distances from the Sun, about 2 billion kilometers apart, revealing that the heliosphere is not spherical. It is compressed on one side by the galaxy pushing back. We are inside a bubble and the galaxy is squeezing it. Then came the magnetic finding that raised the most eyebrows. When Voyager 2 measured the interstellar magnetic field beyond the heliopause, it aligned far more closely with the heliospheric field than anyone had expected. Most models predicted a collision of conflicting magnetic environments. What Voyager found was closer to coherence. The fields connected, and that implies our local region of the galaxy has a structured, organized magnetic architecture that extends well beyond our own star's influence. We are not adrift in magnetic chaos. We are embedded in something ordered. There is also something harder to explain neatly. As Voyager moved through the outer heliosphere, its instruments detected high-energy particles, moving in directions and at velocities that didn't fit the standard models. Non-thermal ions with energies implying they had been accelerated by processes we don't fully understand. The termination shock, where the solar wind first slows dramatically before the heliopause, wasn't sufficient on its own to account for the energy levels being measured. Something in the boundary region was adding energy to the system. What exactly scientists are still working out. In a way, the edge of the solar system turned out to be a particle accelerator, an active zone where solar and galactic environments collide and exchange energy, where physics operates in conditions no laboratory on Earth can replicate, and our only instrument in that region is a spacecraft built in the early 1970s, running on about 22 watts of decaying plutonium, still transmitting. Voyager 2's signal now takes over 18 hours to reach Earth. Every piece of data it sends has spent most of a day traveling through space before a human can read it. Power is the limiting factor now. Both probes run on plutonium generators that produce less electricity as the fuel decays. NASA has been systematically shutting down instruments to extend the mission, making difficult choices about what to keep alive as the power budget shrinks year by year. Eventually, the transmitters will fall silent. The probes will continue moving through interstellar space as dark objects, invisible and unreachable, carrying their records for millions of years. Those golden records are worth thinking about for a moment. Copper discs plated in gold attached to both spacecraft, encoded with sounds chosen to represent Earth. Whale songs, ocean waves, a human heartbeat, music from dozens of cultures, greetings in 55 languages, mathematical diagrams explaining how to decode the disc. It is one of the most philosophically loaded objects ever constructed. A message written with no certainty anyone will ever find it, sent across distances so vast that the civilization that built it may not exist by the time it arrives anywhere. Both records are now in interstellar space, moving through the same compressed, magnetically structured boundary region Voyager mapped. In roughly 300 years, the probes will reach the inner edge of the Oort cloud. It will take another 30,000 years to pass through it entirely. But right now, both spacecraft are still functioning, still transmitting, still doing science at the frontier of the solar system, and what they found there changed our understanding in ways that are still compounding. The heliopause is sharp, not gradual. The heliosphere is asymmetric, not spherical. The boundary region is energetically active, not passive. The galactic magnetic field aligns with ours in ways nobody predicted, and beyond the edge, there is structure, layers, complexity, a dynamic interface between our star and the galaxy that we are only beginning to understand. We still don't have the complete picture. There are open questions the data raise that haven't been answered yet. That is not a failure. That is what real discovery looks like. You find something, and it turns out to be more complicated than you expected, and that complexity points toward the next set of questions worth asking. Two objects are drifting through interstellar space right now, moving away from us at around 55,000 kilometers per hour. They carry the physics of four giant planets: the magnetic corkscrew of Uranus, the lightning of Jupiter, the impossible geysers of Triton, and they carry a gold disk that is also a question. The most patient question humanity has ever asked. Is anyone out there? We may never know, but right now Voyager is still talking, and the edge of the solar system, that sharp, layered, magnetically complex frontier where the sun ends and the galaxy begins, is no longer theoretical. We measured it. We know what it looks like, and somehow the story still isn't over.